Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Aisyah binti Shimaso and I will be presenting about our project which is improvement of porosity and lattice morphology on the mechanical performance of titanium alloy spinal cage. Okay, here is the six content of the presentation today. Okay, let's jump to the first slide which is introduction. Spinal cage are critical in the spinal fusion procedure to stabilize the spine and encourage bone growth. Okay, the spinal cage are important implant used in spinal fusion surgery to keep the spine stable and help new bone grow between the vertebrae. The traditional solid titanium cage are mechanically strong but not too stiff. It's key stress shielding. The conventional titanium cage are very strong, but they are stiffer than natural bone, and this stiffness difference can cause stress shielding, where the implant absorbs too much load, reducing stress on the bone and slowing bone growth. For the next point is about advance in additive manufacturing is allow a customized porous structure to the better mimics bond mechanics. Next is about tolerating porosity and geometry may optimize load sharing and enhance on saturation. Okay, for the result will show the increased porosity enhance the biological environment for bone ingrowth but decrease in mechanical strength. Is optimizing the cage design achieve a balance between mechanical stiffness and morphological feature to improve oscillation and reduce subsidence. Mean that the purpose of the research is to study how change the porosity and the shape of the titanium alloy that it can affect the strength and the ability to work well with the bone tissue. Okay, for the next slide, we'll talk about the problem statement, which is got three problem statement. First one is solid titanium cage are too stiff, leading to stress shielding and poor bond integration. Next is high porosity improve biological integration but can compromise mechanical strength. Lastly, lack of cooperative insight on how the different lattice type and porosity level affect structural performance in the spinal cage. In our project, only one objective, which is we investigate the molecular behavior on spinal cage with different lattice morphologies. Okay, next slide, we will talk about the scope of study. In this study, we focus on the titanium alloy material, which is it can fabricate using the additive manufacturing, laser powder bed fusion. Okay, for the simulate, we can simulate three different type of the lattice structure, which is diamond, troy, and tetradrals. For the performance of the finite element analysis and the experiment to compare the stress distribution and deformation under the axial loading. Okay, let's talk about the literature review. Previous study showed the porous cage reduce stiffness mismatch and the promote bone in ingrowth. Porous spinal cage help the implant behave more like natural bone. This reduced stiffness mismatch, which is when the implant is too stiff and it takes most of the load, causing stress shielding and weakening nearby bone. Okay, next, morphology play the significant role, which is in for diamond has isotropic properties, joint has the smooth curve, and the tetradrals has the high stiffness to weight ratio. The shape morphology of the lattice structure affect both strength and biological behavior. However, a few comparative studies analyze porosity morphology interaction quantitatively in the same content. So, this study also filled the gap by systematically analyzing the mechanical response. Many studies only look at the porosity level or lattice shape separately, very few study directly compare with how the porosity and morphology together with influence mechanical strength and biological performance in the same analysis. On the left is the overall flowchart of this project lah. The way we conduct the project begin with modeling and fabrication, which focus on the evaluating the mechanical performance of the spinal cage based on the interplay between morphology and porosity. From the foundation, we developed 3D modeling of the spinal cage with three lattice for morphology fabricate with titanium material through the LSS process. The porosity control at the 50%, 60%, and 70%. The experiment, next is the experiment using the universal testing machine, which is compression machine. The load we apply on the axial compressive load, which is seven Newton, and we analyze one Venus stress, total deformation, and factor of safety. Lastly, we develop comparison metric on the mechanical performance and the morphology porosity interplay, joint and or orthotic thrust. Now we are reached at the key result, stress distribution. The first result show on your right show the equivalent one value stress of the spinal specimen from FEA. The one value stress show the where the spinal cage is more likely to fail by measuring overall stress on the cage under loading. From the graph, specimen 6 has the higher stress, which means it has the chance to stress concentration on in the design. Um, Other than that, the specimen 5 has the lower stress, showing better load distribution and stress design. Next graph on the below show the young modulus stiffness increase from specimen 0 to 5, but the drop sharply in specimen 6. The drop sharp because of the design chain high porosity, which make the cage less rigid and weaker. Okay, for the key result information and safety, based on the first picture on the left, send image at the 50 time magnification for the specimen 1 and 2. And the second on the right picture show the same image on the 50 time magnification for the specimen 7 and 8. Okay, for the totals, total deformation increase with porosity in all cases. Balance, curtain lattice and porosity combination provided better balance between deformation and stress distribution. For the factor, all design maintain a factor of safety less than 1, indicating mechanical adequacy. Okay, we got four discussion to discuss. First one is the mechanical behavior is strongly covered by the lattice morphology and the porosity level. Second is high porosity reduce stiffness but geometry modulate stress pathway. This study suggests that Optima should not focus on the factor alone, but rather the synergy of the geometry and porosity. Lastly, the finding provide a framework for future spinal cage design that mesh both mechanical and biological requirements. Now we already reached at the conclusion. All three lattice morphology exhibit from stress and deformation response under action load. This study showed the 3D printing allowed the precise control of the porosity and the shape of the titanium spinal cage. Porosity is very important for balancing bone compatibility and the mechanical strength. Cage with about 70% porosity, gerard-like design, gerard-like design and the rough surface give the best result for the bone growth without losing strength. Future research should include tests in living tissue and explore special surface coating to improve bone bonding. Okay, now we already reached at the at the last slide, which is future works. The first is about the fabrication of the prototypes using additive monitoring. Second, mechanical testing under cyclic fatigue and multi-directional loading. Lastly, extension to dynamic loading condition. That's all from me. Thank you. Bye bye.